course where we are trying to understand how to prove that some problems are difficult to solve, right? So we've been seeing algorithms mainly from the point of view of designing fast algorithms or correct algorithms for a variety of problems, and designing techniques to develop algorithms, right? And we have been alluding to the fact that there are difficult problems that we don't know how to solve, right? So it's important to know when you have a new problem, you try your algorithmic techniques and then they don't work, or many people have tried. So how do you figure out whether it's our lack of cleverness, or it may be that things are actually really hard, right? So that's you need to know that so that we can say, okay, the reason I'm not able to do any better than what I think of naturally is because it's really a hard problem, right? How do you prove that, right? So we normally, proving that you cannot do something is hard, right? Lower bounds are hard, right? Proving that there is no algorithm is very hard actually, right? We have very few techniques because algorithms can be so complicated and clever. It's hard to prove that there is no such algorithm for some problem, right? So that's generally the case. So what we do is we do it indirectly, right? So what Lenny did on Thursday is show you in a certain way that once you know that some problem is hard, for example, halting is hard. How do we prove halting is hard? Okay, there is a proof using diagonalization. It's not too hard in that setting. We get a seed problem that, look, halting is hard, right? Now, once you have that, you can prove other problems are hard by saying that, look, if you can solve this problem, you can solve halting, right? That's the idea of reductions, to show hardness rather than to use reductions to actually develop algorithms. Both are important, right? We use reductions to solve problems. You can also use reductions to show that some things are not solvable or some things are hard, okay? And in particular, we'll be discussing this class of problems called NP and NP complete problems because they are common in practice and they are all over the place. So the right level of reduction is a little bit more technical than simply saying that there's a reduction and we need to get to that point. So, okay, so we've seen this many times. What is a reduction from problem X to problem Y? It's a transformation of X to Y, right? Or an algorithm for X using an algorithm for Y, right? And typically we try to use reductions to solve problems. Okay, I know how to solve shortest path, and if I can model my problem as a shortest path problem, that's good, right? And then I can use an existing algorithm. But this part of the course, we are trying to use reductions to show that something cannot be done, right? Okay, that's the flip of the direction, and so we need to be careful about that, right? Okay, so for languages, we'll come back to this. So to make our life simple, we will work with decision problems rather than optimization problems, okay? Because the proofs are a little easier, it's simpler than if you try to work with optimization problems. It's also there is some technicalities with optimization problems which make life a little hard in this regime. So we'll mostly focus on decision problems, right? The decision problems are problems where the answer is yes or no, right? It's not like, compute the shortest path. We were thinking about the decision problem. We want to know, given a graph and some number L, is the shortest path from S to T less than or equal to L, right? That's a decision problem rather than saying, find me a shortest path. That's more of a search problem or an optimization problem, right? So decision problems are a little easier to think about and reason about. So if I have a decision problem X and a decision problem Y, what's the reduction from X to Y? It's really an algorithm, right? What does that algorithm do? It takes an instance of X and spits out an instance of Y, right? That's what we do when we take a problem and reduce it to a graph problem. What do? We take a problem, that instance of what we want to solve, and transform it into a graph, right? So in general, a reduction is just basically an algorithm which converts an instance of one problem to an instance of another problem. And then, so what's the point of that? So that we can use the algorithm for the other problem to solve what we want to solve, right? Of course, in practice, you may have a more complicated reduction where you use it as a black box, you have a subroutine. But this is a restricted kind of algorithm, right? Where you say, okay, look, I take one instance of x and just the algorithm will spit out one instance of y and then just invoke the algorithm for y. So it's a very simple type of reduction. So why would we want to do a reduction? So that we get an algorithm for x, right? Okay. So how do we prove that the reduction is correct? Why do we want to do the reduction? So that we can use the algorithm for y as a black box, right? We don't want to open the algorithm for y, right? So how do you prove that the reduction is correct? Well, just like, why should the reduction be correct? That means we want to solve x, right? But we are taking an instance of x and spitting out an instance of y. And then we are using the black box for y to solve our problem, right? So to prove that the reduction is correct, we don't have to worry about the correctness of the algorithm for y because that we assume is correct. What we need to make sure is that we are transforming x to y properly, right? Otherwise, the reduction doesn't make any sense, right? So what does it mean to make sure that the reduction is correct? Like we did with graphs, we need to know that if the answer to the instance of x is yes, we should transform it in an instance of y so that the answer is also y there, right? And if it is no on x, it should be transformed into instance of y so that it's no, so that we can actually use the algorithm for y and get a correct answer for x. That is what it means for the reduction to be correct. Okay? Yeah? I mean, don't worry about the technicality. If it is very natural if you do the following, right? I transform my problem from what I want to solve to another problem and then use a black box for that problem. Why should it work, right? If you think about why it should work, you should have this property, right? You should make sure that this process of transforming x to y makes sense. Otherwise, why are we doing it, right? What does it mean to make sense in the context of decision problem? This is the property we want, right? That the yes instances of x become yes instances of y, no instance of x become no instance of y. And then, once we have that, we can use the black box for y to get our algorithm, right? Pictorially, it looks like this, right? Our reduction transforms an instance of x into an instance of y. So this is an algorithm actually, right? And then we use a black box for y. And if this says yes, we say yes. If this says no, we say no, right? So this is the point of a reduction. And so this we assume is correct. So all we have to worry about is why this is correct. Okay? Yeah? We've seen many examples of this already in graphs. And any questions about the high level idea of using reductions? Yeah? Seems okay? Yeah? Makes sense? Okay. Okay. All right. So normally what we're trying to do is like, look, I know how to solve this problem y, and so I want to solve x, so great, if I can have a reduction, I have an algorithm for x, right? Now we want to go the other way, right? What is it the other way we want to go is that if we want to prove that y is a hard problem, and if we can show that an existing hard problem reduces to our problem, then our problem must be hard, right? Because what we're saying is that if you can solve our problem, you can solve a hard problem. So it must mean that our problem is also hard, right? So that's the purpose of this. Reductions can allow us to do that also. Okay? So when you're trying to prove hardness, our problem becomes y, and an existing hard problem becomes x, right? When we're trying to solve an algorithm's problem, when we want to use an existing thing, our problem becomes x and the existing algorithm becomes y. So that's the difference, right? Okay. Is it clear? Okay. 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 So clearly this is saying that if we have a reduction, what it says is that x can be solved if y can be solved. So how do we kind of write it notation wise? We'll write x less than equal to y to kind of say that x is easier than y, right? What does it mean? X is easier than y means that, oh look, if y can be solved, x can be solved. So x should be easier than y, right? Yeah. So there's an ordering we put, right? The flip of this is y is at least as hard as x, right? Okay, let's do some examples, And why are reductions interesting, right? Reductions are interesting because, I mean, they can let us do many things and save our time by not inventing new algorithms for every new problem. But they're also, I mean, this is a more surprising thing about reductions and pre-completeness stuff, that seemingly very different problems can be reduced to each other, okay? It's surprising, right? You'll think, this has nothing to do with that, but you can reduce one to another, and it's quite an amazing, some feature of how one can encode in many different ways the same problem, okay? And we'll see some very intricate reductions, and hopefully you'll understand why reductions are important, okay? Okay. So let's see. We have all seen the independent set problem multiple times, right? What is an independent set problem? I give a graph, and a set of vertices is independent if there are no edges between them. And the problem we would like to solve here is find me the largest independent set in the graph, right? That would be a natural optimization problem, right? So in this graph, for example, these three vertices form an independent set because there are no edges between them, right? And there are many other independent sets too, right? You can this and this form an independent set of size 2. So this is an independent set of size 3. Okay. Now what is a clique? A clique is a set of vertices such that all pairs have an edge between them. Okay. As the name suggests, is a complete graph, right? So what's a clique in this graph? This is a clique, right? This is also a clique. Every edge forms a clique of size 2, right? A triangle is a clique of size 3, right? You can have a clique of size 4, right? Okay, are the notions clear? Okay, okay. And also same problem, if I give a graph and say, find me the largest clique in the graph, right? Or largest independent set in the graph. So they are interesting problems, they have many applications. So independent set is, given a graph and an integer k, does G have an independent set of size at least k? So here see, we are interested in the underlying optimization problem, but how do we convert it into a decision problem? By adding this extra variable, right, k, and saying, does the graph have an independent set of size at least given number k, right? Does it make sense? And you can convert most optimization problems into this form, right? I want to maximize something or minimize something. How do I convert it into a decision problem? You add an extra parameter like shortest path, right? I want to solve the shortest path problem and say, look, I give you a number and say, is the shortest path no more than this given number, right? Length. Right? So once you have the solution to this, how can you get back to optimization? If I gave you an algorithm for just the decision, how will you get optimization out of that? Suppose I only gave an algorithm for this, but you want to find the largest independent set. How will you do it? Yeah? Yeah, I mean, if I gave you an oracle for this, right, and an algorithm just which gives you yes or no, you can find the largest independent set by trying all possible values of k, right? K equal to 1, k equal to 2, k equal to 3, and at some point it will say, k equal to 100 is true, but k equal to 101 is not true, right? That means that you know that 100 is the right answer, right? Yeah, but what is a better search than this linear search in general? You should try binary search, right? Why? Because here, the range is between 1 and n because it's numbers, the answer is between 1 and n, so even trying n possibilities is polynomial. But take shortest path problem, right? If the edges have lengths, the answer could be between 1 and something which depends on the bit representation of the numbers, right? So then you should use binary search so that you actually get a polynomial time algorithm. So this linear search doesn't always give you polynomial time algorithm. So you should binary search, okay? Right? I mean, it's also more efficient even in this setting. You'll only use it log n times, right? Okay, clique is the same thing, a graph and an integer k. Does G have a clique of, I should say have, at least k, right? Now the question is, are these related in some way, right? Does one reduce to the other? So if we want to make a mental model, reductions help us make a mental model. Are these related to each other? Are they not related to each other? Is one easier than the other, right? How do we figure that out, right? So I want to claim that I can reduce independent set to clique and vice versa too, actually. They're really the same problem, right? So how do you reduce independent set to clique? So what does it mean to reduce independent set to clique? It means that if I have an algorithm for clique, I should be able to figure out an algorithm for independent set. Okay. So remember, I don't know the algorithm for clique, it's just a black box, right? So my reduction should transform independent set into clique, right? At least they're the same graph problems, right? They're not completely different things, right? They're graph problems, right? So they're somewhat related, okay? So how will I convert independent set to clique? So what does that mean? That means that if I have an algorithm for a clique, I should be able to get an algorithm for independent set, right? Yeah. How will I do that? Let me put everybody knows what independent set and clique. Does this graph tell you something? Yeah, no, doesn't tell you anything to some extent. Yeah. Yeah. So I mean, there's a very simple reduction, right? So I want to solve independent set in a graph G, right? Okay, what is an independent set in a graph G? It's a set of vertices which don't have any edges between them. What is clique? All edges should be there in that set, right? A clique. Okay, so how will I know whether the graph has an independent set of size k in a graph? I claim if I complement the graph. What is complementing a graph? Taking the graph, removing the edges and putting all the non-edges, right? For every pair, if there is an edge in the graph, I remove it. If there is no edge in the graph, I add it, okay? So given a graph, the complement is obtained by flipping, right? Taking any pair which doesn't have an edge and adding that edge and removing all the edges. Now what happens then if I do that? If a subset of vertices formed an independent set in the graph, in the complement what do they form? A clique, right? Okay, and vice versa, right? That if there is a clique in the complement, that means that that set of vertices form an independent set in the original graph, right? So my claim is the reduction is very simple, right? That if I say here is a graph, right, and I can flip it, right? What does I mean flip it, right? I have to make sure that I change all the edges. So this is the complement of the graph. Okay. So algorithmically, what are we doing? If I want to know that a graph has an independent set of size k, I complement the graph and give it to the algorithm for clique and say, does it have a clique of size at least k? If the answer is yes, I will say yes. If the answer is no, I will say no, right? You believe that the reduction is okay, correct? Yeah? It's intuitive? Yeah? Okay, but you have to be a little careful in proving this, that you may need to make sure that if the original graph G had an independent set of size k, then the complement has a clique of size k, because the yes, why would you say yes to a graph with given G and k in the independent set problem? Only if it has an independent set of size k, right? Now you have to convince yourself that the complement has a clique of size k and vice versa, that if the graph has a clique of size k, its complement has an independent set of size k. Simple enough? Yeah? So that's what it means to do a transformation, right? We reduce independent set to clique. Can you convert clique to independent set? It's the same reduction, right? They're the same problem basically, right? You take G and you flip it, right? So what we have shown is that basically the reduction relies on this lemma that G has an independent set of size k if and only if the G complement has a clique of size k, right? The if and only if is important for the correctness of the reduction. So we have shown that independent set is less than, reduces to clique, which means that clique is at least as hard as independent set, right? Clique also reduces to independent set, right? But the same reduction, right? So because they're so simple, they're so related to each other. So then they're basically roughly equivalent problems, right? But that doesn't always happen, right? Okay. So one of the things is that how long does this reduction itself take? Okay. How long did we spend in this? How long does this reduction take? given remember reduction is an algorithm, right? What does it do? It takes an instance of independent set. What is an instance of independent set? G and K, right? Yeah. And then it transforms it into an instance of clique, right? What is that, right? It is spitting out, what is it spitting out, this reduction? The complement of G, right? Yeah. And an integer, right? What integer did it spit out? The same K, right? Okay, how long does the reduction itself take? If I start with a graph of n vertices and m edges, how long does it take to create the graph of the complement graph? I mean, at worst in n square time, right? More or less it spend n square time because either the complement or the original graph has roughly n square edges, right? So it will take n square time, right? Yeah? Does it make sense? Yeah? It's very easy to do, right? Okay. Okay. Now, I'm going to point, here is a problem from our DFA thing, right? So, I give you a DFA and I ask you, is the language of the DFA everything? The sigma star. Okay, so what does it mean? I give you a description of a DFA and ask, does the DFA accept all strings? Does that make sense? How will you solve that problem? I want to know, I give you a DFA, right? What do I mean I give you a DFA? I have to give you the DFA in the sense of the description of a DFA, right? I have to tell you the number of states. I have to tell you, what else should I tell you? Sorry? I have to tell you the transition function, and I have to tell you the final states, and I have to tell you the start state, right? Okay, roughly what does it correspond to? What does the DFA, what is specifying the DFA correspond to, right? It's some kind of a graph, right? I mean, I kind of specify it as a graph or a table, right? I give that to you, right? So there are n states, here is a transition function, here is the alphabet, here is the start state, here is the final state. And I want to know, does it accept everything? How will you solve it? Yeah? No, I want to find an algorithm. It's a very simple algorithm to solve it. Yeah? Yeah, right, okay, you're a little bit more careful. Every state reachable from S must be an accepting state. Yeah? A DFA M accepts every string if and only if every state reachable from the start state is an accepting state. Yeah? Because if there is any state that you can go from the start state which is not an accepting state, I know that I can get to that state and that string won't be accepted, right? Okay? Yeah, does it make sense? So you can use a simple graph reachability to test. It's a graph reachability question, right? I look at the start state and say what states are reachable from S. If all of them are accepting, DFA accepts all the strings. Otherwise, there is at least one string that is not accepted by this DFA. Yeah? So you can reduce it to graph reachability and you can solve it in linear time. Yeah? Very simple algorithm, right? Agreed? Okay, that's the power of reductions, right? We are using reductions to easily solve something which looks like a complicated problem because it's a DFA. DFAs are simple to argue about. Anything about DFA you can understand, right? Turing machines are complicated because they have a huge state and they can go into loops and do all kinds of funky things, right? But Turing machines are algorithms. So a very rich model of computation, so we can't reason about them. So DFAs are easy. Okay, this is easy. Okay, we check if M has any non-reachable non-final state. What about the same question for NFA? It's a little bit more tricky, no? NFA reachability is not so obvious, right? Because why? I mean, the acceptance condition of NFAs is trickier, right? I can't simply, it's not a deterministic behavior, so the fact that there is a non-reachable final state, non-final reachable state from S doesn't mean that that string cannot go to some other accepting state, right? Yeah, it's a bit harder to understand NFAs, yeah? But can we still solve it? Yeah, we can solve it because we can convert it to a DFA and then apply the algorithm for DFA, right? Yeah? So what's the problem? What's the only problem with that? It's an algorithm, it works, yeah. Exactly, right? The DFA that we get from an NFA can be of size exponential in the original DFA, right? So it's not what we call an efficient reduction. Okay, so the previous problem, if I give you the DFA, my running time of the algorithm was what? Just linear time, right? You can just check, some details, but in linear time, you can actually check whether the DFA accepts every string. But if I give you an NFA, this algorithm which goes through DFA is not efficient. Okay, does that make sense? Okay, but remember this is a reduction, right? We reduce the NFA universality to DFA universality. Yeah, by converting NFA into a DFA. But the algorithm for the DFA is linear time, right? But the resulting algorithm, the end-to-end algorithm, is not linear efficient, right? Why is that? Because the reduction is not efficient, right? The reduction took a small instance of a DFA and NFA and could potentially give me a big instance of a DFA, right? So we don't want that, right? Because that doesn't preserve efficiency. Okay, so that's basically what you have to be careful about, and in fact we don't know. You may ask, wait a second, this is not a very efficient algorithm. Is there an efficient algorithm for NFA universality, right? Maybe there's a more clever algorithm. Why are you doing it through DFA, right? And it turns out that it's actually p-space complete, and we don't think there should be an efficient algorithm. Okay, I'm not telling you what p-space completeness is, but we know it's not an easy problem, right? But the point I want to make is that the reduction takes exponential time, and we don't like that, right? So we say that the reduction is efficient if it takes polynomial time. Okay, we are interested in efficient reductions, and so if the reduction itself takes polynomial time, we say x reduces to y in polynomial time and put a p there. Okay, does that make sense? That we put a p to distinguish the fact that it is not an arbitrary reduction, but it is a efficient reduction. Okay, the running time of the reduction should be polynomial in the input size, then we say the reduction is efficient. So what is the advantage of polynomial time reductions? The advantage of polynomial time reductions is that if your reduction runs in polynomial time and the algorithm for y runs in polynomial time, this black box algorithm runs in polynomial time. Polynomials compose, right? Okay, so if you had an efficient algorithm for y, which means there's a polynomial time algorithm for y, and the reduction itself is polynomial time, this entire algorithm runs in polynomial time. Yeah, so we want that, right? Otherwise, if this reduction takes exponential time, even if this takes polynomial time, the entire algorithm takes exponential time. Okay, so we don't want that. So we say that. Okay, one important thing. Actually, let me ask an example, right? So this is something that we have tried to emphasize in graphs also. Let me ask you the question here. Suppose the running time of this algorithm is n square. The running time of this is n cube. Okay, what is the running time of the entire algorithm? Sorry. Okay, so when I say n cube of the running time of this, what does it mean? Sorry, come again, I can't hear you. Okay, this n and this n are not the same, that's why I'm trying to be careful, right? So when I say that running time of this algorithm is n square, what does n mean there? Size of its input, right? If I give it an input of size n, it will take n square time, right? Okay, when I say the running time of this reduction is n cube, what does it mean? If its input is n, it takes n cube time. Okay, okay, now I ask you, what is the running time of this entire algorithm? Is it n cube, n square, n to the 100? Okay, I'll multiple choice. N square, raise your hand. Okay, nobody wants to raise their hand. N cube. Be bold, raise your hand. N cube, okay. N to the 4th. N to the 5. N to the 5. N to the 6. Okay, N to the 10. Okay, all right. The right answer is n to the 6th. Why? Yeah, but so I mean, it's not about just adding or multiplying numbers, right? We have to understand what it means. What does it mean that, so I want to know if the size of this input is n, how long does this algorithm take, right? If the size of this input is n, what is the size of this problem that I could potentially generate? Because it runs in n cube time, it could generate a problem of size n cube. But then I have to run a quadratic algorithm on that input, right? Okay, so I could have this algorithm takes n cube size on a n cube size instance, it may take quadratic time. So the running time of the algorithm will be n cube square, right? So that's n to the 6th. Okay, right? So that's why when we do these graph reductions, we say, what is the size of the graph you're creating? As a function of the original input, right? Maybe you start with the input of size n, but you may create a big graph. And then you're running some linear time or quadratic time or some other algorithm on that, right? So it's important to compose this properly, right? It will be a polynomial time algorithm, but what is the precise polynomial? You have to actually look at the calculations, right? Okay? Yeah? Yeah. Good question. So the fact that this takes n cube time doesn't tell you what the size of this is, right? But I know that it's no bigger than n cube, right? Why can I tell you that if I take n cube time, I cannot create more than n cube stuff, right? So the size of what I get here cannot be more than the running time of my algorithm. So it's an upper bound. It doesn't mean that, it'll actually take n cube time. That's a good question, right? If I actually know that this algorithm always produces something which is of size only n, then my running time is n cube plus n cube plus n square will still be n cube. So it depends, right? I mean, it's a crude analysis, right? Okay, so but it's still important to know roughly what happens here. Okay, so all right, good. That is the efficient algorithm. So let's do more reductions. So polynomial, this is just to say that polynomials compose nicely. Okay, transitivity of reductions, efficient reduction. If x reduces to y and y reduces to z, x reduces to z, right? That makes sense? Yeah, it's algorithmically, it's very simple. If y reduces to z, what does that mean? That means that having an algorithm for z gives me an algorithm for y, right? X reduces to y means that having an algorithm for y means I have an algorithm for x, right? So if I have an algorithm for z, I can first use this algorithm to have an algorithm for y, and then use this reduction to get an algorithm for x, right? And because polynomials compose nicely, if this is efficient and this is efficient, I'll still get an efficient algorithm. The polynomial is increasing potentially, but still polynomial time. Yeah. Okay. Transitivity is very, very important because you can chain reductions like we have already done to get many new algorithms, right? Okay. Vertex cover. So now more reductions. What is vertex cover? I think we have seen it briefly. I'm not sure. What is a vertex cover? It is a subset of vertices such that they cover all the edges. Okay, what does that mean? For every edge, I should have at least one vertex in my subset. So these are a subset of vertices which cover all the edges. Okay, so for example, all the edges have at least one blue vertex incident on them, right? Yeah. So that's called a vertex cover. Of course, I can take the entire vertices, then that will form a vertex cover, but that's not very interesting, right? That's big. So I want a small vertex cover. So the optimization problem is, what is the smallest vertex cover you can get in a graph? Yeah. So I'm saying, okay, can I get away with 2 vertices in this graph? How do I know that I can't get away with 2? Well, that's an interesting question, right? You can try all possibilities or something like that. We'll see some other techniques, but so that's the optimization problem that you're interested in, and we'll see why there is some connection to independent set. So okay, the vertex problem is given a graph, an integer k, because it's a minimization problem. We're asking, is there a vertex cover of size at most k? Yeah, yeah, because remember it's a minimization problem, right? Okay, I want us to relate independent set and vertex cover. So what does that mean? I want us to see that if we can solve independent set, we can solve vertex cover. Well, they don't look related on the face of it, right? Okay. So let's see if you can, this figure will help you. Is blue a vertex cover? Okay, what is this red then? Okay. Okay, now with that insight, can you see how to reduce, say, independent set to vertex cover? Remember, one is a maximization problem, one is a minimization problem. So some flipping has to happen in some way. Okay. So what is the problem I'm trying to solve? I'm trying to solve the independent set problem. It is given a graph, an integer k. Does it have an independent set of size at least k? Okay. I want to maximize this set of independent vertices. Give people a second. If blue is a subset of vertices which is a vertex cover, what should be the rest of the vertices be? Yeah, why is that? I mean, not from the this graph in particular. If S is a vertex cover in a graph, I claim V minus S must be independent set. Let's see, why? Can there be an edge between those two vertices in V minus S? If there is, then that edge is not being covered by the blue guys, right? Yeah, because see, if there is an edge here, it cannot be covered by the blue vertices, right? Yeah? All right? So if S is a vertex cover, V minus S must be a independent set. Yes? Yes or no? What about the converse? If S is an independent set, what should V minus S be? If this is S, what should V minus S be? It should be a vertex cover. Why? Because there are no edges here, right? Since I take everything outside, all the edges must be incident in one of those vertices. Yeah? Okay? Okay, so the lemma here is that if you take a graph, S is an independent set if and only if V minus S is a vertex cover. Is the lemma okay? Yeah? No, okay. So I'm saying that, if you claim that, say I give you a graph, right? And say, okay, you claim that this is a vertex cover. These four vertices cover all the edges. Yeah? Then I claim that, look at all the other vertices which are not in S, there cannot be any edges between them. That should be an independent set. Why? If there is any edge between here, then these vertices cannot cover that edge, right? Yeah? If you claim that this covers all the edges, then there cannot be any edges in this set. Yeah, so V minus S must be an independent set, right? Yeah? Okay. All right. Now suppose, this is actually an independent set. If S is an independent set, the rest of the vertices must form a vertex cover. Why? Where are the edges? If this is an independent set, the edges are either here or one edge might be going from, some edges might be incident here, but the other endpoint must be here, right? If this is an independent set, I cannot have an edge here, right? Then since I'm taking all these vertices, they must cover all the edges, right? They'll cover the edges between themselves, and they'll cover any edge which is going to this independent set, right? The only edges they cannot cover are in between this, but that's an independent set, there cannot be any edges, right? So the claim is that S is an independent set if and only if V minus S is a vertex cover. Okay? So now knowing this, how can you reduce independent set to vertex cover? So what this is saying is that in any graph, the sum of the vertex cover and its complement must be n, right? Okay. So in independent set, what are you trying to do? You're trying to maximize the size of the independent set. What does it give you in the complement? not in the graph, but V minus S must be the smallest vertex cover, right? S is a maximum independent set if and only if V minus S is a minimum vertex cover, okay? All right. So my claim is this: G has an independent set of size greater than or equal to K if and only G has a vertex cover of size less than or equal to N minus K. Yeah? Does it follow from the previous lemma? Right? How can I have an independent set of size K? Well, that means that I must have a vertex cover of size at most N minus K, no? Yeah? Look at the complement, take the independent set of size K. The rest of the vertices must form a vertex cover, right? Which means that the size of the vertex cover is at most N minus K. But it's if and only, right? Yeah? Knowing this, how will you reduce? Okay, now we know this, how will you reduce independent set to vertex cover? What does it mean? I give you a graph and K, and I want to know, does this graph have an independent set of size at least K? What should I do? No, remember it's a decision problem, right? So what should I do? I should take, my reduction should take the graph and K and spit out what? Another graph and another number and feed it to the vertex cover algorithm, right? Yeah? So what, knowing this, what should I do? What should the reduction be? Sorry? What about the graph? Okay. No, but remember, see, the first thing is the input to a problem should be well defined, right? It can't be just be a number, it has to be graph and it's the same graph. No, you don't have to flip anything, right? To see, there is no complement here. G has a independent set of size greater than or equal to K if and only G has a vertex cover of size less than or equal to N minus K. It's the same graph. I take G and K and feed G and N minus K to the vertex cover algorithm. Okay, if I want to know if the graph has independent set of size 1000, I know it can have an independent set of size 1000 only if and only if the vertex cover is of size at most N minus 1000. How will I check that? I have an algorithm for vertex cover, right? So I have to check whether the graph has a vertex cover of size at most N minus 1000. I can do that. I give the graph and say N minus 1000. Is there a vertex cover of size at most N minus 1000? If it says yes, I say, yeah, the graph has an independent set of size 1000. If it says no, I know that there is no independent set of size 1000. That's it, right? So once you have this mathematical fact, the reduction is completely trivial. Take G and K and spit out G and N minus K, where N is the number of vertices. Okay? Okay, you shouldn't think of it as spitting out. You should think, okay, if I know that the graph has an independent set of size K, then how will I check that? I'll take this graph and ask the vertex cover algorithm, does it have a vertex cover of size at most N minus K? If it says yes, I know the graph has independent set of size K. Yeah? Okay? So independent set and vertex cover are closely related to each other, right? It requires some basic understanding of graph theory here. It's not, okay? So that's the reduction, right? Okay, how will you reduce clique to vertex cover? How will you reduce clique to vertex cover? Sorry? Okay, you should say, I'll convert to G. I know how to reduce clique to independent set, and I know how to reduce independent set to vertex cover, so I should be able to do it, right? But I'm asking you directly, how will you do it, right? Just now knowing the two reductions, what does it mean? So if I give you G and K, what does this composition do? Yeah, it first flips the graph, complements the graph, and then gives N minus K, right? Okay? But that's direct reduction, right? It takes G, makes a complement of it, and also does N minus K, right? So that's the reduction. Okay. Sounds good, right? Okay, now we are, so we saw some basic reductions, right? They require graph theory and stuff. But the most important problem in here that we will discuss is satisfiability, right? How many of you have heard of satisfiability? How many of you have not heard of satisfiability? That's better. Okay. You probably have seen satisfiability, it's just that you don't think of it as satisfiability. When you do digital logic and stuff, this is really what you're doing, right? You're doing circuits. Okay, satisfiability is a very simple problem, right? It looks very simple, innocent problem, right? So what is satisfiability? Basically, it is I give you a Boolean formula of a certain type, and I want to know, can I satisfy this formula or not? Okay. What is that particular form? So remember, we are interested in Boolean formulas, so they have variables, n variables, x1, x2, xn, right? And they're Boolean variables, that means they can only take 0 or 1, true or false. Right? And we have formulas of the form, this is called conjunctive normal form, where this is an AND of clauses, where each clause is an OR of literals, okay? So what is a literal? A literal is either a variable xi or its negation, right? It could be x1 or not x1, right? We are allowed to use not of the variables. A clause is a disjunction of literals. I think of it as an OR of literals, right? x1 or x2 or not x4 is a clause, okay? What is a formula in CNF form? It's just a proposition formula which is a conjunction or an AND of a bunch of clauses, okay? This is a CNF formula, okay? Everybody understand what this Boolean formula looks like? Yeah? You take a bunch of ORs and then AND them together, right? What is the meaning of this? You want to say, I want all of these clauses to be satisfied, right? That's what the formula is true if all these clauses are true, but you have a choice within each clause how to satisfy it because it's an OR. Yeah? Okay? So, now we'll say that the CNF formula is called 3CNF if all the clauses have exactly 3 literals. Okay? It's a restriction, right? In the previous case, I didn't care how many literals it had, 1, 2, 3, 100, 2000, right? Here, all of them should have exactly 3 and you cannot have repeated literals, right? I cannot have x1 or x1, that's not allowed. That's cheating, right? Okay, they should be different literals, right? Okay, clearly 3CNF is a special case of CNF, right? Because I'm restricting, right? Okay, what is SAT? I give you a SAT formula and I say, is it satisfiable? Okay, that is, can you put zeros and ones for the variable so that what happens? All the clauses should evaluate to true, right? Because in AND of clauses, right, we want to know whether it's true or not, right? Okay, here is an example. If I give you this formula x1 or x2 or not x4 and x2 or not x3 and x5, it's easily satisfiable, right? Why is it satisfiable? You can put x1 equal to true, x2 equal to true, and x5 equal to true, and I don't care about the rest. Then if I said x1 equal to true, this clause is satisfied, right? This clause is satisfied because x2 is true, and this clause is satisfied because x5 is true. I don't care about the rest. Yeah, there are many ways of satisfying. What about this formula? Is it satisfiable? I claim this formula is not satisfiable. Why? Because for any assignment to x1 and x2, at least one of these clauses cannot be satisfied, right? Because I have all possible combinations. There's one combination which will both of them will turn out to be false. And that particular clause cannot be satisfied, right? Whatever choice I give you for x1 or x2, one of these 4 guys will not be satisfied, right? Agreed? So that's it, right? That is satisfiability. I give you a formula, and is it satisfiable or not? So what is the importance of this problem? Why do you think this problem is interesting? Being computer scientists, why do you think this problem is interesting? Yeah. Any thoughts? Yeah. But why? I mean, that's true, but why is that? So when you learn, do digital logic, right? What do you learn? How are your computers made, right? What is the building blocks of your computers? Logic gates, right? That's the reason why this problem is interesting, because anything you want to do on your computer is basically logic, right? Your whole, take your finite computer, right? Your whole CPU is just, billions of logic gates, right? So it's effectively logic drives our computation, right? Even though we think of computation as numerical things, really logic is driving it, right? Okay, and so logic basically captures all our computation. So it's in that sense, it's circuits. I mean, another way of thinking of logic is that we build our computers out of circuits, right? And circuits are equivalent to formulas. That's what you kind of learn in 233, or right, at least a little bit, right? That you convert circuits to formulas and formulas to circuits, and really they're the same. One is a different programming language of view of the circuits, right? So even though it looks innocent, this is they capture everything effectively, right? So this is a fundamental problem, right? And not only is it, if you want to do verification, okay, let me skip this. Okay, so what I want to do is to show you. So intuitively, you will believe me, and I'll state a theorem without proof that SAT is a hard problem to solve. Okay, what does it mean, a hard problem to solve? How can you solve SAT, by the way? It's not too hard. I mean, if I give a formula and say, is it satisfiable, what is the brute force thing you can do? You can try all possible assignments to the variables, right? And how long does it take? It's exponential in the size of the number of things, so it is not, but we don't have any other efficient way of solving it, right? And we believe there is no efficient way of solving it other than just trying all possibilities. In the worst case, people solve large SAT instances in practice efficiently based on some special cases. But in the worst case, we believe SAT is a hard problem. Okay, how is SAT different from 3-SAT? Well, SAT can have some long clauses, right? What I want to prove to you is that even though 3-SAT looks like a restricted version of SAT, 3-SAT is as hard as SAT. Okay, what does it mean? I want to show you that I can reduce SAT to 3-SAT. Okay, does that make sense? Yeah, that 3-SAT is as difficult as SAT. How do I convince you? I say, look, if you can solve 3-SAT, I can solve SAT, right? So what does it mean? How can I do that via reduction? So what does it mean to reduce SAT to 3-SAT? Yeah, what does it mean? No, so in the sense of reduction, what should my reduction achieve? Yeah. Yeah, so what does it mean, that equivalent expression? Yeah, so more formally, what is the input to the reduction? No, input to the reduction is a SAT instance, right? It's a formula on SAT formula. What should the output of the reduction be? A 3-SAT formula, right? See, what does a reduction do? A reduction transforms one problem to another problem, right? What does it mean? It should take an instance of the first problem. What is the instance of a first problem here? SAT. What is the instance of SAT? It's a formula, right? In SAT form, right? It should convert it to an instance of what? 3-SAT. What is that? A formula which has a restriction that all clauses are of size at exactly 3, right? So a reduction is a transformation, right, from SAT formula to a 3-SAT formula, such that what should happen? What's the point of the reduction? That I give it to a 3-SAT box, right? And if the 3-SAT box can solve it, then I can solve the original problem, right? So what is the property I'm looking for? That if I start with a SAT formula, I should spit out a 3-SAT formula such that the original formula phi is satisfiable if and only if phi prime is satisfiable, right? Okay, that's the meaning of the reduction, right? I want to convert a SAT formula which can have many different sizes of clauses into another formula which has only size 3 clauses such that if this formula is satisfiable, that formula is satisfiable. If this formula is not satisfiable, that formula is not satisfiable. Right? I should not disturb the satisfiability of the formula, right, by doing this. So that I can then use a black box algorithm for 3-SAT. So it proves to me that 3-SAT is as hard as SAT, right? As long as I can make sure that the algorithm runs efficiently. Okay? So how will I convert a SAT formula into a 3-SAT formula? What is the difficulty? Why is it not a 3-SAT formula? Why is this not in 3-SAT form? Because this has how many clauses, or how many literals? 5, and this has only 1, right? That doesn't look nice, right? So you want to make it look nice, I mean, this is fine, right? But in terms of 3-SAT formula, it doesn't look nice, right? So what we'll do is we'll say, aha, to make it look like a 3-SAT formula, I should make sure that I don't have any clauses which are too short, right? 1 or 2, I should make them look what? 3. If it is more than 3, I should kind of convert them into size 3, right? But I can't do arbitrary junk and get that out, right? Otherwise, it won't preserve correctness. So how can I do that? Okay, let's do it one by one, right? Okay? All right, so the easy case first. If I have a clause with 2 literals, how can I create a clause with 3 literals? Okay? All right? That's already not completely obvious. I will add a new variable, okay, and replace this clause with these 2 clauses. Does that make sense? Okay, what did I do? I added a new variable. Remember, I'm allowed to increase the formula a bit, right? I'm not keeping the same variables. I'm actually increasing the variables. Okay? All right? So what did I do? I took a clause with 2 literals, added a new variable. U is not one of the old variables. It's a new variable, right? And I made this into 2 clauses now, not 1 clause, right? Okay. Now, do you see the logic behind this transformation? Yeah? Why did I put U here and not U there? Because whatever choice you have for U, right, one of them has to be 0, one of them has to be 1, right? Okay. So you're worried that adding this new variable will help this old formula by making it satisfiable when the old formula was not satisfiable. But by adding U here and not U here, these 2 clauses, how will they be satisfied? If and only if L1 or L2 is satisfied, right? Because maybe you can help this clause, but it can't help this clause also, right? Okay? Yeah? Okay, if I have a big formula where I have this clause and I replace that clause with these 2 clauses, I want to claim that the new formula with these 2 clauses is satisfiable if and only if the old formula is satisfied. Do you agree with that? Yeah, sort of. Yeah. Remember, I don't touch any of the other clauses. I took one clause which had 2 literals and stuck a new variable like that, and I also stuck a new clause with the not of that variable, and I threw out the old literal. Now I did this as a local transformation, right? I only changed one clause by adding one new variable. Okay, and I want to claim the old formula is satisfiable if and only if this new formula is satisfied. Okay. If the old formula is satisfiable, I can just take the same assignment. I don't care what I put for U. It will satisfy these 2 clauses and all the old clauses, right? Yeah. And the converse is a little tricky, right? I want to claim that if the new formula is satisfiable, then the old formula is also satisfiable. Yeah. Does that make sense or no? This transformation made sense? Okay. Do you want me to do a longer example, or this is okay? Okay, this is okay. Okay. So now that is for one. I mean, this is the easy thing, right? I have a clause of 2 literals. What if I had a clause of 1 literal? We can do the same trick. We add 2 variables now, not 1, U and V, and I replace it with 4 clauses. Remember, if C is a clause with a single literal L, now I add 2 variables U and V, and I have all 4 clauses: U or V, U or not V, not U or V, not U or not V. Remember, we already said that whatever assignment to U and V, one of these guys won't be satisfiable, right? Yeah. How can you satisfy these 4 clauses? You can satisfy these 4 clauses if and only if L is true, right? Yeah. Does that make sense? It's the same idea as this, except that now because I want to increase the size by 2, I create 2 variables. Yeah, is it okay? No? This doesn't make sense? Yeah. This seems reasonable? Yeah, okay. So that's how we change what? If you have short clauses, we can make them size 3, right? Using this trick, right? Okay, remember, for each such clause, you have to add more variables, right? Yeah? Remember, if I have a short clause of size 2, for each such clause, I have to create 1 extra variable, right? That's okay, because the number of variables I'm adding is not too big, right? It is simply the size of the old formula, yeah? Then I get rid of it, yeah? Okay, so this is how you take the old formula and make the short clauses long clauses, yeah? Now I have to tell you how to take long clauses and cut them down, right? Yeah, then if I can do that, then I can do that for the, okay. Now the other idea is, suppose I have a clause with 4 literals, okay, and I don't like it because it's too long. I want to make it look like 3 literals, right? So it's L1 or L2 or L3, no, so in fact I have 5 literals. Here is how I do it, right? I basically, what I want to say is that I want to do it in the following way, right? And I say, oh look, I'm going to think of this as a new variable u, and I'm going to basically replace L4 or L5 by u, and I create a new clause L4 or L5 or not u here, okay? So I took a clause with 5 literals and changed it into 2 clauses, one with 4 literals and one with 3 literals, okay? All right. Now I want to claim that this clause is satisfiable if and only if these 2 clauses are satisfied. Again, the same trick, right? How can you satisfy this clause if and only if these 2 clauses are satisfied? Okay, this is actually more intuitive than it looks, right? So what I'm trying to do here is, it's just variable replacement, right? I have L1 or L2 or L3 or L4 or L5. So I'm basically writing this as L1 or L2 or L3 or U, and U is equal to L4 or L5, right? I'm just replacing L4 or L5 by a new variable U, right? And I'm just, if I can allow you to use clauses U equals to, right? This is logical, right? I just replaced L4 or L5 by a new variable U, and then I wrote U equals to this, right? That makes sense? Yeah? All right? Does this, I'm replacing this, I'm just calling this a new variable U, basically. Yeah? And I just say U equal to this. This, if I can, right? But I don't have this, right? I can't write equal to in my formula. But I'm claiming that this will exactly do the same thing, right? How will you write U equal to A or B, right? Okay, you can create it into CNF form by complicated things, but I want to say that this effectively does the same thing. Okay. Okay. To argue this, can these 2 clauses be satisfied if none of the L1 to L5 is true? If all of them are false, what happens to one of these 2 clauses? Cannot be satisfied, right? Yeah? If all of them are false, whatever you set U to, if U is true, this will be satisfied, but this won't be satisfied, right? Right? Agreed? If U is false, then this won't be satisfied, even though this is satisfied, right? If all L1 to L5 are false, there is no way both of these clauses will be satisfied, whatever you set U to. Is that clear? Okay, but the converse is also true, right? In the sense that if at least one of them is true, then both these clauses can be satisfied. Okay, how? Yeah? No, so U is a new variable, right? Remember the formula is U can be set to whatever it wants, right? That's important, right? We change this formula into this formula, U gets freedom to be set to 0 or 1, right? If L1 is true, I can set U to false, and that way L1 will make this clause true and not U will make this clause true, right? right? If L4 is true and the others are false, I'll set this one to be true, and then L4 will satisfy this and U will satisfy this, right? So I claim this, these two clauses are satisfied if and only if at least one of this is satisfied, okay? So what this trick will allow me to reduce a clause of size k into two clauses, one of size k minus 1 and one of size 3, right? Now to change this 4 to 3, what should I do? I should repeat the trick again, right? I should take these two variables and use a new variable v and say L1 or L2 or v and L3 or u or not v, right? So this trick allows me to reduce a clause of size k to two clauses, one of size k minus 1 and 3. If k minus 1 is 3, I'm already done, otherwise I have to do it again, right? So I can do it again and again and again, and then I'll be done, right? Okay, so that is the idea, and it's very simple at some level. And here is an example. So this is the original formula, and I want to convert it into a 3-sat formula, right? What did I do? I do it one by one, right? So how should I replace this clause? It has size 2. Remember, that's the first trick we did, right? So we add a new variable z, and so we have this or z and this or not z, right? That is what we did with this clause, right? And then this we don't have to touch, right? Because it has exactly 3, right? That we don't touch. What about this? We have to take this size 4 clause and convert it into 3 and 3, right? So how do we do that? We add a new variable for these things. So I'll call it y1. So it's not x2 or not x3 or y1, and x4 or x1 and not y1, right? I'm going from 4 to 3 and 3, right? Otherwise I have to do 5 to 4, 3 and, okay? And now how about this clause? We add two new variables, right? Remember, x1 becomes x1 or not. I replace this one clause, a clause with one literal into 4 clauses with 3 literals, yeah? I add two new variables, right? All this, at each step the variables have to be new, right? In fact, the process is sequential, right? You do one clause at a time basically, right? And each time you're adding some new variables, yeah? So by induction you can prove that, this process preserves the satisfiability of the formula. In one step, what formula you get is satisfiable if and only if the previous formula is satisfiable. So you change these things by induction, you will get the property that the first formula is satisfiable if and only if this last formula is satisfied, right? And we convert it into 3-sat form, right? Does it make sense? It's a simple logical transformation, okay? And you have to easily check that this transformation is polynomial time. That, at each clause we add one variable, and it's not hard to check that this transformation takes polynomial time, okay? So that's it. So you can convert sat to 3-sat using this thing, and you can ask, why did we get to 3-sat and not 2-sat? What is 2-sat? What is 1-sat? 1-sat is every clause has one literal, right? That's easy, right? Why is 1-sat satisfiable? Can you check whether 1-sat is satisfiable or not? What is 1-sat? Every clause has only one literal. You have no choice, no? If every clause has one literal, you have to set it to true or false, because if you want to satisfy it. If you get a contradiction, you can't satisfy it, right? If x1 or not x1 are both clauses, then it's clearly not satisfiable. Otherwise, it is easily satisfiable, right? Because if there is no contradiction, you can just, every clause is determined, right? If the clause is x3, there is no choice. If you have, there is no or in there, right? So you can just set to x3. What about 2-sat? 2-sat is tricky, right? 2-sat is already is not so obvious. What is 2-sat? Every clause has 2 literals or at most 2 literals. It turns out that 2-sat can be solved in polynomial time. Okay, so you need to. So 2-sat is easy. 3-sat is already hard. Okay, why is 2-sat easy? It's not so easy to say. Okay, I mean, you can reduce. You can actually. There's a very simple algorithm using strong connected components and stuff like that. I'll point you to it. It's cute algorithm. Why is 2-sat easy but 3-sat hard? Okay, so there's actually an algorithm here if you want, right? So you will kind of believe me that somehow SAT is hard because it's logic and it captures computation in some way, right? I can convince you by showing Cook-Levin theorem, but it takes too long and everybody falls asleep, right? It's a very intuitive proof, but it takes too long. So the point about why we care about SAT is SAT is hard, and you have to believe me that SAT is hard, and then I will show you reductions which convert SAT into independent set. Okay, so what does it prove to you? That if you can solve independent set, you can solve SAT basically. Now that's surprising. Okay, that came as a big surprise in the 70s when that happened, because it doesn't look like SAT looks like anything like independent set, right? It's like converting basically some very different problems to each other, right? How can you capture logic using independent set? And turns out that you can, and that's why very strange looking problems can be reduced to each other, right? And that's why it's interesting, both algorithmically and to prove that okay, but first I have to tell you a little bit. I mean, I know it's the end of the class, so I'll tell you a little bit, and I will catch up about that next lecture. But I just want to introduce at least Sudoku to you, right? And see what's common about Sudoku and SAT, and if it is okay. That's hopefully at least somewhat interesting to you. You can have some coffee table, party conversation or something, right? Why do I study NP-completeness, right? Okay. So so here is a set of problems, right, which we discussed today. Independent set, vertex cover, set cover. We didn't cover set cover. We'll come back to this. SAT, 3 SAT. Thing is, we don't know any efficient algorithm for any of these problems. The only thing we know how to solve them is brute force, right? Exponential time algorithm, right? Okay, and these are a small number of examples of many problems where is an easy brute force algorithm, but no efficient algorithm that we know. Okay, so what should we do? Right? So when if you have a lot of problems where you're having trouble finding efficient algorithms, one thing you could try to do is like maybe they're all related to each other, right? Right? If you can prove that they're all related to each other, at least we have reduced our space of understanding to like, okay, they're all related to each other. If you solve any one of them, then okay. But before you even get there, you can ask, is there something common about them, right? Other than the fact that we can solve them by brute force, right? You can ask, and there is something interesting about them that I want to tell you about. One thing that they have in common is that if I give you a solution, you can easily check them. Okay? You may think that this property is trivial, but it's not. Okay? All right. So here is a simple idea. If I want to convince you that a given formula is satisfiable, what can I do to you? Give you, right? I can give you a satisfying assignment, right? And you can easily check that, oh, this formula is satisfiable because I gave you satisfying assignment, you can verify easily, right? Yeah? Okay. What about independent set? I want to convince you that the graph has an independent set of size 1000. How can I convince you? I can give you a subset of vertices, and you can say, oh, there are 1000 vertices here, and they don't have any edges in the graph, all right? Okay. What about homework? Okay. I give you homework, right, and then I can, it's solving the homework may be hard, but I can convince you that there is a solution to it by giving you the solution, right? You can hopefully at least read the solution and say, yes, that is correct, right? Okay. So these problems have this feature like Sudoku, right? You're sitting on a plane and you're struggling with this, and then you look at the back of the thing, right? And but they all have this feature that if I give you the solution, there is an easy algorithm that can check whether that solution is correct. But there's a more subtle feature which is not so obvious, is that not only is the solution easy to check, What is it easy to check? There's an algorithm which is efficient, right? Given the problem and the solution, instance and the solution, it can efficiently check whether it's actually a valid solution or not. Second property which is also important is that the size of the solution is not too big. Yeah, that's very important, right? What is the size of a Sudoku solution? It's not bigger than the original problem, right? Not too much bigger than the original problem, right? Okay. So there are two properties that are important for these problems. One is that if I give you a solution, you can easily, there is an algorithm which can easily check that this is a valid solution. Okay. Second property is that the size of the solution is not too long compared to the size of the original problem. Okay. That's also important. That is usually overlooked, but both are important. Okay. So these two properties create a class of problems called NP. What does NP stand for? Non-deterministic polynomial type. Okay. I did not define non-deterministic with Turing machines because it's a pain, right? But this is very easy to understand, right? This property of a problem that you can easily check a solution and the solution is not too long compared to the original problem. That's the same as non-deterministic polynomial type. Okay. All right. And all these problems have that property, and these form a class of problems called NP. Okay. And so that is what we are trying to understand, right? And SAT also is in that class, and we'll define what it means to be a hard problem. And the big open question is, why don't we have a polynomial time algorithms for this problem class, right? And that's the big open question. Okay.
For reducing SAT to SAT, when you're condensing, like if you have like 4 literals and you're condensing it to 3, so when you replace like L4 and L5 with U, does that mean like U is equal to L4 or L5? Like, do we define that?
No. It's I mean, formally you can do that, but no, that's the right way of thinking about it. But it's easier than that because, I mean, you can actually, I mean, what I'm saying is that you can actually, you can write, it's easy to see that if you replace L4 and L5 by U and then add a clause U equal to L4 and L5, then that's a correct reduction. Okay, now how do you convert U equal to L4 or L5 into, you can easily convert that into clauses, but you get more clauses. But this is a faster way of doing the same thing. Okay. It's a more compact way of doing exactly.
Okay. Thank you.
So I'm still curious about like the lab for the undecided question. So basically the format is to embed some.
I don't think about the format. If you think about the format, you will probably not understand what is going on.
Well, it seems like it's trying to like say, if you can solve this problem, then you can solve some undecidable problem.
Yes, exactly. Yeah, and what is that undecidable problem? Just basically halting.
Right. But
I mean, it's okay. Here is the thing. You need to kind of understand it intuitively more than, if you don't understand the intuition for it, then you're basically going to struggle, right? And the way to understand that intuitively, it's actually so simple that it's really about understanding what is the problem you are being asked to, you're trying to understand, right? Not so much the reduction itself. Okay. So look at the auto-grader example class. What is the auto-grader example, right?
So if the auto-grader can.
So what is the auto-grader supposed to do? What is its input? It's always important to understand what is the input of the auto-grader.
A piece of program.
Yeah, it's a program, right? And what should it do?
Say it's a program.
Print hello world, right? Okay, why is that hard? What do you think is hard? I mean, it seems like a trivial problem, no? Yes. But why is that hard, you think?
Because don't know what actually is inside of it.
Yeah. Okay. Yeah. More formally, what can you do? Yeah. So yeah, you don't know what's in the program. No. Well, So what did Lenny do in lecture? Okay. So the formally, okay, it's true that you don't know what's in the okay. The formal claim is that if you had an auto grader for print hello world, then it will enable you to solve any interesting thing that you want, right? That it will enable you to solve halting.
Right.
Okay, how did you do that?
Okay.
Not the halting problem. That's the thing. Okay, that's why I'm trying to be slow, right? You get an algorithm for the halting. So the input of the halting problem is some piece of code, and you want to know where to halter. Right? Okay. So you want to know an algorithm for that. Okay? And we know there is no such algorithm, right? But I claim that if you had an auto grader for printf hello world, then what can I do? I can solve halting as follows. Right? Remember, the input to halting is what? Some piece of code, right? So what I will do is I'll create a new piece of code which will run the old piece of what you want to check. I'll put it inside and then do print of hello world and then wrap it up into another big piece of code, right? Now this code, what happens with this code? I didn't do anything. I took the code you want to check and just created a new code. I just put print of hello world at the end of it. Okay, so I think it's good to be concrete, right? Rather than abstract. Okay, so here is the thing, right? See, I mean, instead of being, it's easy to get lost in the syntax, but suppose, if you do this, right? Suppose you want to know some specific thing like, gold bar, right? Whether it will halt or not. Okay? But you only had an auto grader.
For the hello world.
But hello. So here is what I will do, right? No, but remember this goldback is a piece of code, right? You have the code for goldback, right? You know how to write goldback, right? You already have the code for it. So what you do is you just do this, right? You create this program, main, and then you say, you call goldback first, then you say printf hello world. Okay, now remember, this is the main, and I'm writing in C, and then you put goldback here, right, the subroutine. So this is now your program, and you give it to autograder. The autograder knows, right? If it says yes, then you know that the goldback has to halt, right? Yeah. But your reduction didn't do anything. It took this code and produced this code. So what it is saying that if you had an autograder for printf hello world, you can solve halting, no? Because goldback could be any program I give you. That's it. You're not trying to solve halting. You're trying to say that if you had an autograder, you can solve halting. This way. Right? So, but then what that means is that you should, that means that if you had an autograder, you can solve halting. So that means you cannot have, so that means autograder will solve, so so, but this is trivial, no? What did you do? You took this code and created this code. That's it. Linear time operation. The reduction is completely trivial.
Well, but like in that case, you would say every column.
Oh, what do you mean? Why do you mean every problem when you said it?
Because for any problem, you can say
No. What do you mean any problem? But the autograder, what is the input to the autograder? Can you reduce it to shortest path? It's true. I mean, okay, we'll see Rice's theorem that any property about what language is a Turing machine accepts is basically undecidable. Yeah, it's true. They're all the same problem. They're all hard because they're all trying to work with arbitrary programs. Okay. See, autograder is supposed to take any program and then say yes or no if it prints up hello world. I say that's too hard because if you want to reason about programs, it is too hard. Any problem which involves reasoning about program behavior is undecided. Yeah, this is a trivial reduction. In fact, all of these reductions look exactly the same.
So can I say any problem there?
No. That is Rice's theorem. We'll come to that. But right now you have to say this way. This looks trivial, but it is important to understand what it is saying. It is trivial. I'm not saying it is not. The reduction is completely trivial. So you have to understand what the reduction is.
So basically, it accepts machine there. Yes.
I mean, more or less. Right? Yeah. If it can understand the program behavior, that means it will solve problems. Right. Like how any other piece of code is. That's all. Making no, actually somebody else's pen. I thought, yeah.
เดี๋ยวพาไปทำลายเนี่ย